Okay, so this is applications of functions. This is showing how functions are useful in real life and showing how the equations we've been learning are very useful and how they can show up. So first, let's start with what is a function. So a function is a relationship between two variables where the input only corresponds with one output variable. So being that it is week 8, a good example are grades. Your grade is a percent and then your letter grade. So if your grade as a percent is our input, you have only one letter grade associated with that. So if I gave you, or if you gave me your percent, I could tell you what letter grade you currently have in the class. It's not possible to have more than one letter grade with a percent. So that is considered a function. We use special notation when we have functions. So instead of y, we use f parenthesis x parenthesis, which is read as f of x when we read that out loud. And we use this just to indicate that it's a function, so it has this special property. What's nice is that it gives us a name. So f is the name of the function. So you can use any letter you want. We usually use F or G. You'll see P and Q as very common ones as well. But you can use names. So you can have area as a function. And instead of X, you can use a different input like S if it's an area of a square. We can use letters for like H for height, and then your input, T for time. So, the most basic function when it's not a real world problem, we usually use f of x, but if it's related to the real world, we start to use letters that are related to the problem, and that makes sense. So instead of using x as your input, you'll use a different letter, and that represents what you're learning about or what you're trying to find. And then your output, if you're trying to find height as your output, you'll use h instead of y. It just gives it more context, and it just makes it kind of easier to understand. So let's start with this example. In the absence of air resistance, the speed s of t in feet per second of an object in free fall is a function of the number of seconds t after it was dropped. And they give us the function or the equation s of t equals 32t. So s of t, that's the output. Our output is speed, and that's why we have the letter S for speed, and it's measured in feet per second. T is the input, and we use T for time, and it's measured in seconds. Now, it's very common to use T for time and measure in seconds. So pretty much if you see a function and T is the input, you can assume, if it's a lowercase t, that it means time measured in seconds. That's just a kind of a guarantee. So we've got 3 parts here. Find s of 1 and interpret the meaning of this function value in terms of speed and time. So the nice thing about function notation is that what's in parentheses is telling you what to plug into the equation. So the equation has t in parentheses, that's our input. So when you see s of 1, that means replace t with 1. So it's just telling us to plug in 1 for t. So s of 1 will be 32 times 1. And when you are finding a function value, you are evaluating, which means you follow the order of operations, and you only work on the right side of the equation. There is no solving. So I keep moving to the right because we are evaluating, we only want to work on the right. And if I keep moving to the right, it kind of helps me do that without wanting to divide, because we're not doing any division here. You're not dividing by anything from the left. You're just multiplying here the 32 times 1. So that gives us 32. And then our units, because this is output of speed, is feet per second. So interpret the meaning is basically saying write this as a sentence, putting it in context of your input and your output values and what you're measuring. So t is 1, so this is at 1 second, or this would be 1 second after it started falling. So after 1 second, the object is falling at a speed, because that's what we're measuring our output at, a speed of 32 feet per second. So that's what this interpretation means, or the meaning of this number 32, s of 1 equals 32, is telling us after 1 second, the speed of this falling object is 32 feet per second. So now we want to find s of 2 and then interpret the meaning. So now t is going to be 2. So s of 2 is equal to 32 times 2, which gives us 64. And again, our units are feet per second. So the meaning is now after 2 seconds, the object is falling at a speed of 64 feet per second. So it's speeding up as it falls. Now, acceleration of this falling object is constant due to gravity, but it does speed up. Now, the third part, a ball dropped from the top of the Willis Tower in Chicago falls for approximately 9.2 seconds. So they're giving us time. So t is equal to 9.2. How fast was the ball going the instant before it hit the ground? So we're going to find the speed at 9.2 seconds and assume that's basically the speed right before it hit the ground, because obviously when it hits the ground, it's no longer moving, its speed is 0. So s of 9.2 is equal to 32 times 9.2. And so now I'm going to grab my calculator to multiply that out. I get 294.4 feet per second. So the ball was going 294.4 feet per second right before it hit the ground. And if you are curious, you can just put into Google, convert 294.4 feet per second to miles per hour. You know, if you want to know what that is in miles per hour, that comes out to about 201 miles per hour. So very fast. Very fast ball. Here's another example. The number of people diagnosed with skin cancer, n of x, so n here is standing for number, can be approximated by n of x equals 45,625, and then in parentheses, 1 plus 0.029x. So for this function, x represents the number of years since 2003. So in this case, instead of using t for time, they're using x, and it's specifically the number of years since 2003. So we have to think about that when we find our answers. So we want to evaluate n of 0, and that's the same thing if you're told to find n of 0. Evaluate and find are essentially the same thing. It means, you know, do the order of operations. So we're going to evaluate n of 0 and interpret its meaning in the context of this problem. And so that is basically saying, do what we did previously. Make sure you're measuring your input and your output when you're explaining what it means. So n of 0 means x is 0, because x is our input here. So I have 45,625 times 1 plus 0.029 times 0. So sometimes instead of moving to the right, you may want to go below like we usually do. And when you do that, We don't put anything to the left just to remind yourself that this is not something we're solving. So 0.029 times 0 is just 0, so this ends up being times 1. And then this gives us 45,625. So this is our output. The output is the number of people diagnosed with skin cancer. And then our input is 0 years since 2003, because X is the number of years since 2003. So this tells us in 2003. So in 2003, 45,625 people were diagnosed with skin cancer. So you may notice that I'm basically sort of repeating the sentences that they're giving us. You know, you're taking whatever it says it represents, you're taking that first sentence, you're just kind of rephrasing it and throwing in the numbers. So now evaluate n of 7. So this is telling us X is equal to 7, and this is 7 years after 2003. So 2003 plus 7 is going to be 2010. So we need to keep that in mind. This is going to be for the year 2010. So we're going to evaluate n of 7 and interpret its meaning in the context of the problem and round to the nearest whole number. So n 7 is now going to be 45,625 times 1 plus 0.029 times 7. So calculator out, I need to multiply that decimal by 7. So we have 45,625 times 1 plus 0.203. So of course we're going to add 1. So 45,625 times 1.203. And then you're going to multiply that by 45,625. 54886.875 is the number I get. And of course, this is number of people. We can't have a decimal amount of people, so we're going to round to the nearest whole number, which would be 54,887, because we have to round up because it's an 8 after the decimal place. So interpret this meaning in 2010, because that's 7 years after 2003. 54,887 people were diagnosed with skin cancer. And there we go. That's our interpretation. Here's a good example that actually shows up in MA105 College Algebra, weeks 6 and 7. You learn about this type of equation. It's a quadratic, as you learned. We did do a little bit of quadratics this week, so you'll see that again in week 6. And then the discussion for week 7 is not for football, but it's for baseball, and it's very similar. So I thought this was great. We can tie this in, and then for those going on to College Algebra, you'll have seen a little preview, and you'll be like, when you get to those weeks, you're like, I saw this already. So a punter kicks a football straight up with an initial velocity of 64 feet per second. The height of the ball, h of t, so h for height. T again is going to be time in seconds. I mentioned if it's a lowercase t, that's what it means. So it says the height is in feet. So this is a function of the number of seconds t after the ball is kicked. So we have this chart. Now the chart is graphing over time. The football is just going straight up. It says a punter kicks a football straight up. So it's basically, it's going up and then coming back down. But when you graph it across time, it makes this nice parabola, and we get this equation. h of t equals negative 16t squared plus 64t plus 3. And you'll learn where that equation comes from in college algebra. It's actually an equation that's related to physics and is a very good model for this kind of thing. So our first part, find h of 0 and interpret the meaning of the function value in terms of time and height. So h of 0 means we're plugging 0 in for t. So our equation is negative 16t squared, so that's going to be 0 squared, plus 64t, so that's going to be 64 times 0, plus 3. So 0 squared is 0, and then you're going to be multiplying by negative 16, so that's 0. 64 times 0 is 0, and we get 3. And our output here is feet. So that's the height. It says the height is measured in feet. So what does this mean? So t is 0 seconds after the ball is kicked. So when the ball is kicked, it's 3 feet off the ground. So that's when the punter is kicking, he kicks the ball when it's 3 feet off the ground. You could visualize that. He's holding it up, and that's approximately how high it is when it gets kicked. So when the football is kicked, it is 3 feet off the ground. So now we want to find h of 2 and interpret the meaning in terms of time and height. So h of 2 now means we're replacing t with 2. So we have negative 16 times 2 squared plus 64 times 2 plus 3. So we're going to have several steps here. First off, 2 squared is 4. So I have negative 16 times 4. And 64 times 2 is 128 plus 3. Then I have negative 16 times 4, so that comes out to negative 64. And I can add the 128 plus 3, which gives me 131. And then if I do negative 64 plus 131, that gives me 67. And this is 67 feet. And if you look at our graph at 2 seconds, you can see that's at about 67 feet based off the graph. And that actually appears to be our maximum. So we have the graph to kind of aid us here to also determine that this is basically the maximum height of the ball. So our interpretation would be 2 seconds after the ball is kicked. After the football is kicked, it reaches a maximum height, and we only know that it's maximum because of the graph. Maximum height of 67 feet. So that's our meaning of this, and we interpreted the meaning in terms of time and height. We've got the time in there, we've got the height, and we added in, what it means. It's the maximum. That's what that graph is kind of showing us, that's the highest point. So now find h of 4 and interpret the meaning. So h of 4 is now we're going to replace t with 4. So we have negative 16 times 4 squared plus 64 times 4 plus 3. And if you look at the graph, it's going to be close to 0. You can see it's not going to be equal to 0 because it hits 0 a little bit off of the graph, but we're going to get something that's close. So 4 squared is 16, so we have negative 16 times negative 16. 64 times 4, 256, and plus 3. So negative 16 times 16 is negative 256. And then we basically I'm just going to notice here, plus 256 plus 3, you can see that the negative and the positive 256 are going to cancel, and our answer is going to be 3 feet. So, and that's what it looks like. It looks like about at 4 seconds, it's back to 3 feet off the ground. So 4 seconds after the football is kicked, kind of squeezing this in, it's 3 feet off the ground. And that's the interpretation. So we've got the time in there, we've got the height. Now this is my last example here. An electrician charges $75 to visit, diagnose, and give an estimate for repairing a refrigerator. If Helena decides to have her refrigerator fixed, she will then be charged an additional $50 per hour for labor costs. The equation for the total cost, C of X, so C standing for cost here, and that's very common. Fixing the refrigerator can be modeled by the linear equation C of X equals 75 plus 50X. So we've learned about linear equations. 75 is that y-intercept, or your starting point. So it's base rate of $75, and then we're adding $50 per hour. And X is the number of hours it takes for the electrician to fix the refrigerator. So a lot of things that we deal with in real life can be written as linear functions, where you've got some base rate and then you have like an hourly cost associated with it. Those are all linear functions. And that's how you'd write your equation to figure out the cost. So we want to find the total cost for an estimate and 3 hours of labor. So 3 hours of labor tells us that X is equal to 3. So we're going to find C of 3. Didn't tell us that, but knowing that we have 3 hours of labor and X is the number of hours it takes to fix, hence the labor, we know that our input is going to be 3. So that's 75 plus 50 times 3. So that's 75 plus 150, which I should be able to do that in my head, 225. I'm going to just double check that my mental math is correct. Double check my 50 times 3. That's, yep, all of my mental math. So the total cost for the estimate and 3 hours of labor is $225. And notice I'm including the units there by having the dollar symbol. If Helena spent $200 on fixing her refrigerator, how many hours of labor was she charged for? Well, we know that 3 hours is $225, so we know that it was less than 3 hours here. We find this out by replacing the cost part of our function with $200. And then we have 75 plus 50x. So now we've got an equation to solve. You just replace the left side with that cost because that's what it's standing for. C of x is the total cost. This total cost is 200. So we're going to solve for x. So I'm going to start by subtracting $75, which gives us 125 equals 50x. And I'm going to just kind of rewrite this here so I can show that we are dividing both sides by 50. And I think that's going to be 5. I just want to double check my mental math. 2.5. Yep. Don't trust my mental math. I don't know why I was thinking 5. Oh, because I was dividing it by 25. I was thinking quarters. So we get 2.5 equals x. So she was charged for 2.5 hours of labor. Now the next question says, what is the domain of x, C of x? So the domain is the values that you would be plugging in, or what the input values are, the values that would make sense for your input. So our input are hours it takes the electrician to fix the refrigerator. We certainly are not going to be plugging in negative, because it doesn't make sense to have negative time. And we're not going to plug in, well, we could have 0, because it could be there, it took 0 hours, he doesn't fix it all. So our domain is going to be 0 and anything larger than that. So we can write this as x greater than or equal to 0 for our domain. We can also write this in interval notation, but that's focused more in college algebra. I'm just going to write it as an inequality that our input values are greater than or equal to 0. And theoretically, our domain, it could go on for, infinity here. You can have like 500 hours. Unlikely, but it is still possible with our equation. Technically, with our equation, we can plug in negative numbers, but when you think about the problem at hand, that doesn't make any sense. So our domain is going to be based off of what makes sense in terms of the problem. So that's going to be values that are 0 or bigger. And then what does the y-intercept represent? I actually answered this at the very beginning. That y-intercept, which is $75, that is representing the base cost, the estimate, without any work. So the y-intercept represents the estimate with no work done. That's what that 75 is, and that's the y-intercept. So that is applications of function in a nutshell. So this whole class, we've been learning about solving equations. You'll be learning about all these different types of equations, how to solve them. Last week, you learned about graphing, and now it's all kind of coming together with your real world problems. Like, we could graph all of these equations, and it makes sense to have these kind of things graphed. For example, the football here, it makes sense to see that and see what it means and what it looks like over time. So we're kind of putting together a lot of what we've done this whole class to see how math really does show up in the real world, and it actually is very helpful. It would be very helpful for somebody to understand how their bill is calculated. And if they have an equation for that, especially if you are the electrician, you can make sure that you have this equation, you just plug in your numbers, and then you can figure out the cost pretty easily. Let's say you are a football coach. You may want to know, how high up does the football go? When somebody's punting, you may want to know what their velocity is, so you can determine, is it going to be high enough to go through the goal? There's a separate equation if you are also looking at your horizontal distance, but you can analyze those numbers based off of knowing their velocity and know, do they need to learn to kick harder so they have a harder velocity? If they're not making the goal, you can take all that account with the algebra. Equations like this they come up a lot in the medical field. There's a lot of people that analyze data in medicine. They'll get equations like this from statistics. So if you have to go on and take a statistics class, that's how a lot of these equations are found, is through statistics or statistical analysis. And you can do linear statistics, you can do polynomial, you can do a whole bunch of different types, but they take the data, they find equations that help you predict the data, and then they use that to make decisions moving forward based off of what the equations say. And then this equation, as I mentioned, that this is free fall. You've got gravity, which is constant acceleration, but this equation, the 32T, this actually comes directly from physics. This is how, at any object, the speed of an object when it falls, it does not matter how much it weighs. The speed is entirely based off of the acceleration due to gravity. This is the speed equation for it. air, the airflow, and you can get some friction with air, which can make things appear like they're falling, at different speeds. But if you're in a vacuum, everything falls same acceleration. They will hit the ground at the same time, no matter how much they weigh. There was Galileo actually did this experiment and proved it. This is the equation that gives you the formula for how fast things are going. And so if you're, curious about physics or all that kind of stuff, you can even kind of figure this out yourself. You can test it out. There's a whole bunch of stuff on the internet of, gathering data to then prove or find this formula. And you see that actually in the real world, yes, this formula does work. It's something that it's a mathematical part of the world. So, functions really do show up everywhere. You'll see these equations, and even if you're not solving this, there are lots of people that are doing things related with functions in algebra. So that's all I've got for you guys, and hopefully you had a really great class, and maybe I'll see you in the next one. Thank you.